Hello friends, in this lecture I am going to talk about many electron atoms, spectral term symbols, spectra of hydrogen and alkali atom and selection rules. Now, what are spectral terms and term symbols? Atom with more than one electron is a complex system of mutually interacting electrons via repulsive Coulomb interaction, and each electron is also under the influence of attractive Coulomb interaction of central nucleus. More complication is added when spin of electrons is also considered. How then one can define state of atom which is same as combined state of all electrons? So, essentially you should appreciate that it is a complex system. There are many electrons, they are interacting with among themselves via electron repulsion, and each electron is interacting with the central nucleus by the Coulomb interaction. If there is only one electron and only Coulomb interaction is considered, then N, L, Ml and Ms are quantum numbers and energy of electron depends only on N. This energy is 2n square fold degenerate, as this we have already seen. Even with two electrons, due to mutual Coulomb interaction and spin orbit interaction, L and S are of each electron not well defined. What we have is capital L is equal to L1 plus L2, capital S is equal to S1 plus S2, capital J is equal to capital L plus capital S, where J is the total angular momentum, L is the total orbital angular momentum, S is the total spin angular momentum. Now, in LS coupling scheme, Ml and Ms of each electrons are not good quantum numbers, but L, S, J are. Something similar happens when the number of electrons is more than 2. It is found that we can with fair accuracy say that stationary state of each electron is determined by its motion under some effective central field due to nucleus and all other electrons. Electron states are still determined by N, L, Ml, Ms quantum numbers, but due to non-Coulombic nature of effective central potential, different L states differ in energy. Higher is L, higher is energy. Degeneracy with respect to Ml and Ms is still retained. In a given atom with Z electrons, allowed states characterized by N, L, Ml, Ms are filled in accordance with the Pauli's exclusion principle. No state can accommodate more than one electron. What we then get is a shell and subshell structure for atom. A given n state can accommodate 2n square electrons because there are n different possible L values, and each L state can accommodate 2 into 12 plus 1 electron corresponding to as many different Ml, Ms states. Now, the general trend is that energy increases with n, and for some n, states with high L have high energy. Sometimes, however, energy of n plus 1 L is equal to 0 state may lie lower than n L is equal to n minus 1 state. For example, energy of 4s is less than energy of 3d. We have a filled shell structure for different n values. First shell is filled by 2, second by 8, third by 18 and nth by 2n square electrons. For a filled shell, sigma ml sigma ms is equal to 0. Sigma ml means sum of our all ml values, sigma ms is sum of all ms values, and this corresponds to L is equal to S is equal to 0, which means that for a filled subshell, the total angular momentum is 0 and total spin angular momentum is also 0. Over and above filled shell, there are some filled and unfilled subshells corresponding to different L values. In carbon atom, there are 6 electrons with 1s2, 2s2, 2p2 configuration. First shell with n is equal to 1 is filled. In second shell with n is equal to 2, S subshell is with L is equal to 0 is filled, but P subshell with L is equal to 1 is unfilled. There are 2 amongst its maximum capacity of 6. State capital L capital S of atom is determined by electrons in the last unfilled subshell. L value is determined by combining different small l values, and S value is determined by combining different small s values of electrons of last unfilled subshell. This is important. We just have to consider last unfilled subshell. That is what is important. General rule for combining two L values L1 and L2 is that capital L can take all values from L1 minus L2 mod to L1 plus L2 with interval of unity. For example, for L is equal to 1 and L is equal to 2, possible capital L values of are 0, 1 and 2, that means 1 minus 1 to 1 plus 1, 0 to 2. General rule for combining different S values S1 and S2 is that capital S takes all values from S1 minus S2 mod to S1 plus S2 with interval of unity. Now, different combinations of capital L and capital S produce different terms, each being represented by capital L, capital S. So, that means capital L comma capital S is a term. For example, for configuration NP and dash P for a 2 electron atom, capital L values are 0, 1 and 2 and capital S values are 0 and 1, then different terms are 2 1, 2 0, 1 1, 1 0, 0 1 and 0 0. For that means each L value is linked with one S value which is 0 or 1. L is equal to 0 when linked with 1 and 0 is 0 1 0 0, L is equal to 2 linked with 1 0 is 2 1 2 0 and L 1 linked with 1 0 is 1 1 1 0. Now, these 6 terms have different energies due to residual interaction which is non-spherical part of electron-electron Coulomb interaction. Capital N capital S of each term further couple to produce different levels represented by 2s plus 1 upper script L and J lower script. These are known as spectral terms of atom. So, you see 2s plus 1 Lj is a spectral term. You see the particular way we write. The capital L is indicating the orbital angular momentum value, capital J is indicating total angular momentum and 2s plus 1 represents the spin value. So, 2s plus 1 Lj is a spectral term for the atom. Possible values of J for the term Ls are all values from L minus 1 S to L plus S with interval of unity. That means, given L and S, we can form possible J values and with the help of L, J and S, we can write the spectral term in the form 2s plus 1 L J. For the term 2 1, possible values of J are 1, 2 and 3, which is very clear because L is 2, S is 1 and J is L minus 1 to L plus S, 2 minus 1 to 2 plus 1, that means 1 to 3. Hence, the spectral terms are 3D3, 3D2 and 3D1. For the term 1 half, possible values of J are half and 3 half. Hence, the spectral terms are 2 P half and 2 P 3 half. Now, 2s plus 1 is multiplicity of states because when L is more than S, there are 2s plus 1 possible values of J. This is why we write 2s plus 1 in the spectral term. When L is equal to 0 and S is equal to 1, there is only one possible value of J. So, multiplicity is 1 and not 2s plus 1 is equal to 3, but by convention this state is also written as 3s1. Now, we talk about hydrogen spectral lines. Experimentalists observed various spectral lines of hydrogen atom. It was found that lines could be grouped into various series and each line of series could be given by a simple relation which involved two integers n1 and n2, one constant and another varying. For example, Balmer series involved n1 is equal to 2 and n2 is equal to 3, 4, 5, 6 for the first, second, third and fourth member of the series. What experimentalists did was how to write a simple formula in which the observed values of the frequency or lambda could be written down. We know that the emission of each spectral line is due to transition of atom from one allowed state having energy E2 to another low lying energy state having energy E1 subject to certain selection rules. Radiation of energy nu is emitted such that E2 minus E1 is equal to h nu. That means, the frequency depends only on the difference of the two energy levels. For example, in Lyman series we have n1 is equal to 1 and n2 as 2, 3, 4, 5. For Balmer series n1 is equal to 2 and n2 3, 4, 5, 6 and so on. We have shown all these lines Lyman, Balmer, Paschen, Brackett, Pfund and Humphrey series, in which one is constant and another integer is varying. We have solved hydrogen atom problem using Schrodinger equation and found that allowed energy for electrons are En is equal to minus 13.6 upon n square electron volt. It is now easy to explain origin of Lyman series which correspond to various frequencies. Nu is equal to 13.6 by h into 1.6 into 10 to the minus 19 into 1 upon n1 square minus 1 upon n2 square. Mind it, here again n1 is constant and n2 is taking all values from 2, 3, 4, 5 onwards. So, the original basis for n1 and n2 representing a series is now obtained from the formula En is equal to minus 13.6 upon n square electron volt, because the spectral frequency emitted is just the difference of two energy states labeled by two integers. Origin of other lines can similarly be explained by assignment of different n1 and n2 values. What you see here is just the energy level diagram of hydrogen atom and various spectral lines. You see the ground state is n is equal to 1, next excited state is n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, and you see all Lyman series terminate at n is equal to 1, Balmer series terminate at n is equal to 2, Paschen series terminate at n is equal to 3, from all n values upward in energy. So, this way we explain the various series of hydrogen spectral atom. Some lines have fine structure, that is two lines close together. For example, two components of first member of Balmer line have been shown, which are due to the following transitions: n is equal to 3, j is equal to 3 half, to n is equal to 2, j is equal to 3 half, n is equal to 3, j is equal to 3 half, to n is equal to 2, j is equal to half. Due to relativistic and spin effects, energy does not depend only on quantum number n, but also on total quantum number j. What you see here is splitting of n is equal to 2 and n is equal to 3 levels of hydrogen atom due to relativistic and spin effects. So, what we are saying is that each level is now simply not characterized by n values, but also other quantum numbers, and this makes a splitting of each line. Further level splitting may take place if we include more interactions, because it is these interactions only which split the lines. Inclusion of interaction of magnetic moment of proton with electron spin angular momentum will split each level into two very close levels, leading to hyperfine structure of spectral lines. Now, you see here we say that here an electron interacting with the magnetic moment of proton, and this interaction will split lines, though this splitting is small. So, it is called hyperfine structure of spectral lines. Now, inclusion of interaction of electrons with fluctuating quantized electromagnetic field removes the degeneracy of levels with the same Nj, but differing in L, and this is called Lamb shift. So, the levels 2s half and 2p half have different energies now. Earlier we have seen that for the same J, the energy is same, but you see here 2s half and 2p half have same J, but because of the using the quantized electromagnetic field, they are separated in energy, and it is called the Lamb shift. Various splitting have been measured with great precision, and this leads to better understanding of the underlying interaction. So, here in this slide you see fine and hyperfine splitting of levels of hydrogen atom. As I told you, hyperfine splitting is due to interaction of proton angular momentum with electron. Spectra of alkali atoms. In an alkali atoms, we have one electron above a closed shell structure. In sodium atom, ground state configuration is 1s2, 2s2, 2p6, 3s1, and 10 electrons in filled shells n is equal to 1 and n is equal to 2 form a negative spherically charged distribution and screen to a large extent the valence electron in n is equal to 3 shell from positive nucleus with charge plus 11e. This screening effect is more for electrons in the excited state with large n values, and it experiences effective nuclear charge of plus E only. Here we are saying that this screening is very important. There are electrons between one electron and the nucleus, and this screening effect determines to a large extent the energy associated with the electron. Now, electron states of sodium atom are determined by principal quantum numbers n, capital L, capital S values corresponding to spectral term 2s plus 1 Lj. Ground state of sodium is 3, 2 upper script S, J values has been suppressed, and excited states in increasing order of energy are as you see on the screen, and spectral lines are grouped into 4 series: principal, diffuse, sharp and fundamental. It is like just as we saw before that the spectral lines of hydrogen atom were grouped in various series, Lyman, Baumer, etc. Similarly, spectral lines of alkali atoms have been grouped into 4 series: principal, diffuse, sharp and fundamental, and it is now up to the theory to explain why these 4 combinations, 4 series have come into existence. Principal: transitions terminating on 3,2s from all higher lying p states in n more than 3. Sharp: these are the transitions terminating on 3 to p from all higher lying s states in n more than 4. Similarly, diffuse and fundamental are various transitions. Here you see on the slide energy level diagram for sodium atom, principal, sharp, diffuse and fundamental spectral lines. Now we talk of doublets in spectra of alkali atoms. All lines in spectra of alkali atoms are doublet because spin orbit interaction term which is proportional to L dot S term. I have already talked about the spin orbit interaction in my previous lectures. Now we can write L dot S because J is equal to L plus S, and from that we can write L dot S is half J square minus L square minus S square. And now you recall that J square is proportional to J into J plus 1, L square goes as L into L plus 1 and S square goes as S into S plus 1. So, J is equal to L plus minus half makes energies of 2S plus 1 capital L plus minus half different because L dot S values are different. So, in here in this slide you see D1 and D2 lines of sodium are produced when 3 2p half and 3 2p3 half excited states of sodium decay to 3 2s half state respectively. You see D2 and D1 lines. So, this is called the fine structure of spectral lines in sodium atom, and D1 and D2 lines are pretty close. That is because 3 2p half and 3 2p3 half states are pretty close. Since alkali atoms behave very much like one electron atoms, their energies can be approximately represented by En is equal to minus Z minus sigma whole square upon n square mu A by Me into 13.6 electron volt, and mu A is reduced mass of electron, Me is mass of electron, sigma NL is screening constant depending on N and L, and Z is atomic number of alkali atoms. You see, we had a simple formula minus 13.6 upon n square electron volts, but we must amend it to take into account of the reduced mass of the electron, and hence the term mu A by Me, and then you must take into account the screening effect. So, the Z goes to Z minus sigma. How much is the screening? It depends on sigma. For sodium atom, Z is 11, sigma NL is 10, for n is equal to 3, L is equal to 2. This means screening is almost complete for this state. Energy of 3,2D state of sodium atom is almost equal to energy of hydrogen atom corresponding to n is equal to 3 state, and sigma NL is equal to 9.155 for n is equal to 3, L is equal to 0. This means that for the same n, higher L values corresponding to better screening because of the large centrifugal potential. Now, we talk of selection rules. In multi-electron atom, we have seen that the state of electrons, which is same as state of atom given by spectral term 2s plus 1 Lj, allowed dipole transition from one state to another is possible only if following rules called selection rules are obeyed. You see, I told you that a frequency or spectral frequency is obtained when atom makes a transition from one state to another state. The question is, can any two states can be connected by this transition? The answer is no. Some rules must be satisfied, and these rules are selection rules. So, the selection rules are delta J is equal to 0 or plus minus 1, and J is equal to 0 to J is equal to 0 is forbidden. That means, the difference of J values as it makes a transition from one state to another should be either 0 or plus minus 1. Secondly, delta L is 0 or plus minus 1. That means, the difference of L values from one state to another is either 0 or plus minus 1, but with the provision that L is equal to 0 to L is equal to 0 is forbidden, because from 0 to 0 is also delta L is equal to 0, but this case is forbidden, and delta S is equal to 0. That means, the two states connected by dipole transition should have the same S value. In addition, delta L is equal to plus minus 1 for electron which makes a transition from one state to another. Now, consider some examples. 2p half to 2s half. In this transition, we have delta J is equal to 0, delta L is equal to minus 1, delta S is equal to 0, and hence it is allowed because of the selection rules I mentioned before. Consider another. 3p2 goes to 1d2. Here delta J is 0, delta L is equal to 1, but delta S is minus 1. So, it is not allowed. We have seen that delta S should be 0. Now, consider this 1s 2s, that means 2 1s 0 going to 1s 1s, that is 1 1s 0. It is not allowed because 2s to 1s transition, in this transition delta L is equal to plus minus 1 is violated. So, basically we are saying that electron making a transition by dipole allowed transitions from one state to another must satisfy certain selection rules, and these rules must be obeyed. In this part of the program, we have seen for multi-electron atoms what are spectral terms, how to designate energy levels using term symbols. Spectral terms of hydrogen atom and alkali atoms can be explained using quantum mechanics, and one finds possible energy states and use selection rules to find out the frequency of the spectral lines. Thank you. I hope you must have enjoyed the lecture.